it is about to come to an end, but he'll be back in July for the Bootstrap meeting. So let's hear what he's been working on with heavy operators and matrix models.
Thank you, Connor. Yeah, so as Connor just said, I'm working on understanding heavy operators in matrix models, and this is work in progress with Andrea Guerrieri and Pedro. Okay, so let me get started. So in large N holographic theories, if you insert a heavy operator, by heavy operator I mean that's something that scales with n squared at large N, then so let's see. Okay, that's fine. Yeah, I'm just worried if it's let me just fix that. Okay. Yeah. So as I was saying, so if you insert a heavy operator in a large N theory, then it sorry. It's a slide. Yeah. So when you do that, you typically get a black hole in the bulk. So the idea is the following. So if you have a non-integrable quantum system and you insert a heavy operator, that, or if you go to a highly excited state, then there is the eigenstate normalization hypothesis, which basically says that highly excited states give you the same correlation functions as thermal ensemble loop. And also, so that's one point, and the other is that in ASCFT, a thermal boundary state is due to black holes.
Excuse me, it just said you were muted. Is that?
That's through the laptop, I think. So, can people on Zoom hear me?
Andre, can you hear us?
I think yes, because I see the audio going up and down on this.
Yeah, then you should be able to respond. Okay. Can you hear us, Andre?
Okay.
Little bit. So you cannot hear us?
Okay. Yeah, I can try to talk.
Okay, if it's bad, just complain so we can hear that it's bad.
Alright. So the idea, as I was saying, is that heavy operators in ASCFT correspond to black holes in the bulk. Okay. So in particular, we know that black holes have no hair, which means that the details of the heavy operator should be.
Now you're going too fast. No, I don't agree.
Okay. With which statement?
Talk about classical black holes or what?
Yeah. I mean the holographic limit, which is large N strong coupling.
You're claiming all heavy operators are the same?
Well, not good, because you have also the supersymmetric things which would lead to. Yeah, so typical heavy operators would correspond to black holes.
Are you claiming the heavy operators have no hair?
Yes, if it's a typical heavy operator.
I don't know what that means. What does typical mean?
Something that is not supersymmetric and heavy.
Well, it should be a statement about
It's
how
not supersymmetric, it has no hair, but
a
it's
high
supersymmetric,
percentage of
yeah.
operators are like
Yeah, because for instance, if you take half the PS operators, they're
No,
doing well
supersymmetric is certainly a special case of a non-supersymmetric.
Yes, but you can
How
have.
can it have hair if it's supersymmetric and not have hair? One is a subclass.
So you can have supersymmetric black holes, in which case again the hair does not exist.
So supersymmetric does not have hair either.
Supersymmetric black holes don't have it.
Do not have hair.
Yes.
But supersymmetric heavy operators?
There are some which correspond to black holes in the bulk. There are some which correspond to other geometries in the bulk, in which case the details of the operator would not.
I think you're saying tautology. You're saying heavy operators which correspond to black holes don't have hair.
Yes.
You don't know which heavy operators they are?
Yeah, that's true. That's true. Yes.
But you also want to say that a typical heavy operator corresponds to a black hole, right?
Yeah, that's
No,
also.
that I disagree with.
If you have a non-supersymmetric operator that is heavy, and you take a typical high energy state from the theory, let's say UN equals 4 and you take a high energy state, in the bulk, that would correspond to a black hole. That's the...
Supersymmetric black hole is a special case of a non-supersymmetric black hole.
That's true, yes.
And if you say non-supersymmetric black holes are typical, then by definition, supersymmetric black holes are also typical. Because
So
it's a
that's
subclass
not
of
true,
the other.
right? No, subclass is not, yeah, subclass need not be different.
So you say somehow the fact that it's supersymmetric gives it air? That's crazy.
I think supersymmetry is not really relevant for this argument. Just a huge.
Okay, but we'll see only examples of yours. That's alright. So this is a bit vague, this introduction, so I'll get more concrete later on. Yeah, so the question that we're asking is, do we see some sort of universality in simple time models, and which are, I'm considering zero-dimensional matrix integrals without space-time. So that's the main question that we want to address here. Alright, so now you could ask what sort of theories should we consider. So if you, for instance, if you just take a simple free Gaussian theory, there is no universality. So then we could ask, yeah, we want some interacting theory, but what sort of interactions? So I'll just list a few holographic theories. So the first one we're talking about is N equals 4 super angles, which is very well studied, and we know that, so okay, that's one example. And then another is the BFSS model, which is a matrix quantum mechanics model, so it has time but no space. And then we also have the ICTP model, which is in fact a model without space or time, but it is conjecturally dual to tiny bulk. Right, so the common feature in...
And you're not going to tell us anything about it, you're just going to say it's a claim, but you're not going to give any argument.
Yeah, this talk is not about ICTP, but we're trying to motivate the...
So I'll let you go through that.
So the common feature in these holographic theories is that you have these sorts of terms. So you have commutator of bosonic matrices squared and then some Newcomb couplers. So okay, so this is interesting. In all of them, this exists. Now, motivated by this, let's consider.
That's because they're supersymmetric. Go ahead.
The commutator is not equal to supersymmetric.
Yeah, no, those two terms that you just described are there because the theory is supersymmetric.
Sure. But I'm going to throw away supersymmetry now and just talk about bosonic integrals.
Okay,
but still,
no reason why those terms should be there. But okay,
well, we'll see. So in 2D, the simplest integral would be something like this: the commutator squared. I don't have any formulas. Could consider this. So x and y are two n by n Hermitian matrices, and we'll apply some coupling. So okay, you consider this, but it turns out that this is not a finite integral.
Why is that called 2D? Sorry.
Oh yeah, okay. So in this talk, I'm going to say number of matrices is the dimension, in quotes.
Okay.
Right. So this is not a finite integral. So you can see this by diagonalizing the matrix X, and when you do that, so you have dx, which now in the change of basis you have little x I at the eigenvalues. U is the matrix of eigenvectors. It's a unitary matrix. And this factor is the Jacobian you get when you go from the matrix to eigenvalues. Right, so this product I less than jx minus xj is often called the one-to-one delta of x. Okay.
So the Hermitian matrices?
Yeah, these are Hermitian matrices. Right, so now you can integrate out the y's. Oh, by the way, here the action simply reduces to this. And when you integrate out the y's, you get a product of these factors, right? It's a Gaussian with product of x minus xj squared. And that cancels precisely the one-to-one squared term, and you just get an integral of 1, which is of course infinite.
Sorry,
Sorry?
Oh, sorry, it's x, y squared. Never mind, forget it.
Yeah. So this integral, this naive integral that you wrote down, is not finite. However, there's a simple fix. If you just introduce a mass term, kinetic term, which is x squared plus y squared, this turns out to be finite, and this is called the Hopper model. And actually, this model can even be solved at large n analytically in terms of elliptic functions at any coupling lambda. That was done in these papers. But we're only interested in the strong coupling limit, where lambda is much bigger than 1, and in that limit things simplify a lot. So we won't try to look at the exact solution, we'll just look at the strong coupling limit. Okay, so now let's try to solve it at lambda going to infinity, and following this paper where they do this. So first we diagonalize matrix X as we did earlier, and this is what we get. So notice that earlier there was no 1 plus here, but now that exists because we have a mass term for the y's. And again, you can integrate out the matrix y, and this is what we get. So this factor is from integrating the y's out. Okay. So this is exact. Now you can go to the larger limit, which is basically take the number of eigenvalues going to infinity. And in that case, you have a density for the eigenvalues, and this is the saddle point equation that you get. So, okay. So this almost looks like the usual resolvent that we get, but modified by this factor. Right. So now we want to solve this equation at strong coupling. So first note that this term which we had in the equation actually is the derivative of the function. So
This would be known to cascade.
sure. Okay.
So you're taking lambda to infinity.
This equation is not lambda. This is finite number. We're going to go take the strong coupling limit in the next slide. This is just the larger limit of this integral. Okay, yeah, maybe if this you have not seen this before, it might not be too familiar, but let me explain what the terms are. So firstly, this is just integrating out the y, which is Gaussian. And now we want to take the variation of the action with respect to the eigenvalues. So this minus x is the derivative of the Gaussian term, right? In the saddle point equation, and then the rest of it comes from varying this term with respect to xi. And we want to find solutions to this. Is that clear?
You said y was symmetric. Do you mean y was symmetric or?
No, it's just summation.
I don't know. Why is the action real?
Because it's, I mean, the eigenvalues are real. If it's a Hermitian matrix.
X. So
Sure. So let me go back maybe one slide. So here, x squared and y squared have real eigenvalues. And the commutator is anti-Hermitian, so it has imaginary eigenvalues. But because the square, it's again real, and the sign makes sure that it's positive definitely. Right. Any other questions about this? Yeah, I can slow down a bit because there's no point in maybe going to function. Stop me if there's something stuck here. Yeah, but anyway, so you have the simple and you take you find saddle point equations for it, and you want to solve the saddle point equations. So the first term in the saddle point equation is something like this, and then we note this fact that this integration kernel that I'm highlighting here without the rho of y, that's simply the derivative of the delta function. And therefore, at strong coupling, we have this identity that the left hand side simply becomes rho prime of x. Okay, so now if we go back and plug it into the saddle point equation, what we get is that rho prime of x is linear in x, which means rho is parabola. Okay, hope that was clear. So we get rho prime is linear, and then we integrate to get a parabola, and then we can actually fix the size of the parabola by comparing with the previous equation. So you get some L equals 1 over lambda to 1/6 power times some numerical factors. So what we have done is at strong coupling, we found that we get a parabola which is vanishingly small in size. Okay, so that's the result. Now we can try to, so this parabola is something that shows up repeatedly throughout the talk. So let's try to first make sure that we're doing the right thing. So what you can do is, we have the saddle point equation that I showed 2 slides ago. You can discretize it and then numerically solve this equation for some large number of eigenvalues xi. So here I'm doing n equals 600 and I'm doing lambda equals 10 to the 4. And I have to go to sufficiently large lambda such that because the expansion was going in powers of this 1/6, which means convergence to strong coupling is pretty slow. For numerics, I need to do large enough lambda. Okay, but when you do that, these blue dots are what I get are the density of the solutions of this equation. Yeah, this is the density. The y-axis is the density and x-axis is x.
Density of what?
Density of solutions of this equation. So I get a bunch of solutions xi. I compute how dense they are.
So did you choose some small binning?
Small binning? No. Okay, here you could do that, but here I just say density is 1 over the separation between here and values. Okay.
Sorry, that was some code words I didn't ask. What are the choices for xi and xj?
So these are n equations for n unknowns, and I just solve them.
So you can solve them?
Numerically, yeah.
Yeah, so naively, they're all different, so you would say the density is uniform. It's just 1 for each value you get, but then a bunch of them are closer together than others. So
Yeah,
that's
exactly. You get this, a bunch of numbers, and then you can ask how close they are. And in fact, as n goes to infinity, it becomes a continuum, and that's this continuum of solutions between -0.4 and
You can do settlement because you're large lambda.
yes, yeah.
Large lambda means.
So at large n, I thought you said very large n, which is why you can do settlements. In fact, I'm keeping lambda to be 10 to the 4, which is some finite number.
So large n, only the saddle, it's classical because it's large n. So
Yes.
just looking at the.
That's right.
Wouldn't it be more convincing if n were larger than lambda?
That's true, but it's just very hard to solve. And also, you could worry that we're not in the proof limit, but because of these powers of 1/6, it's actually fine. I just checked that it doesn't change with changing n. It's converged.
Why is it the powers of 1/6?
That's what we get from this. It's just this. So we solve that.
Is there a boundary condition from the equation?
It's a very interesting question. A boundary condition?
Boundary, because
Ah.
solving the differential.
No. Actually, so I went a bit fast here, but so rho prime is linear in x, which means rho is quadratic. And then there is an unknown constant, but that is just fixed by normalization because the density should be normalized to 1. So there's no unfixed constant. Okay. Anyway, so this was the vacuum. Are there any other questions about this? If not,
Can you compute the correlation between diagrams?
you can. Sure, you can study that, but we did not. But I guess you mean like instead of density, you compute like 2 point density. We did not do that, but you can derive probably results for that. What we're more interested in, maybe the next slide will make it clear what we are interested in. So let me clarify what I mean by heavy and light operators. So the integral measure, which is the Van der Waals and the action, they both scale as n squared. And therefore, if you insert an operator into the integral, if you insert some invariant into the integral, that scales with a lower power of capital N, then it does not compete with these two terms. And therefore, it does not change the saddle point configuration. For instance, if you take a single trace operator, trace x to the n, for little n being order 1 or order n even, that's an example of a light operator. Or even few determinants that also will not change the saddle point equation, cannot compete. Right. So then the point is, if you put a light operator, you just find it by evaluating the light operator at the saddle points. For instance, if you have trace x to the n, you just evaluate this thing with rho of x fixed by the saddle point equation, and that's what the result is. Similarly, you can find the determinant.
Why do you have to strongly interact with those? You said it, but I don't know. So why was it important that lambda was very, very large?
Yes, because at some point here, yeah, this is a strong company. I'm sorry. So saddle point equation was this, right? And this thing simplifies when lambda is very large. In general, it's fine to solve, but when lambda is very large,
Compared to what?
1. Yeah, there's no energies or anything, it's just numbers here.
So nothing carries dimension, right?
Yeah, it's just. These are 0 dimensional integrals. Okay.
Is there any physical interpretation from these heavy and light operators? Like they represent some kind of particle?
Yeah, that's the idea. That if light operators, if this was a holographic theory, not some simple matrix integral, then light operators would be equal to string modes, and heavy operators would be equal to black holes and other geometrics.
Big brains.
Big brains would also be light because light in this sense because it's order. It's not going to change the background.
So that's why.
A deep brain does not change the background. Gravitation solution is still perturbable if you have one deep brain.
Yes, these three types of operators you mentioned. Harish is calling them light, heavy. Pedro calls them light, heavy, huge.
I guess, yeah.
And the original terms, the x squared and y squared terms, are those somehow universal or and other? I'm just trying to understand.
Sorry, I understand.
You couldn't just have the interaction term, you have to have some other terms.
Yeah, I had to put the mass to make it a finite, the kinetic term.
They don't, their choice is completely.
Yeah, you can rescale the matrices such that kinetic term is normalized to 1, and then there's only the coupling that is the free parameter.
But think about the quadratic terms that could have besides x squared and y squared.
Yeah, you could study those as well. Sorry?
They don't do anything if you add the other two.
It would, yeah, so that's the sort of question that we want to address in fact. Is there a universality or does it matter what sort of actions you consider?
And the answer is?
The answer is yes for the large class.
The answer is it does matter or it doesn't?
It does not matter. Okay, yeah, so maybe I should speak up. Sorry. I should definitely speak up. Right, so as I was saying, light operators, you just evaluate them at the saddle point. And heavy operators, as I was saying, because they scale at the same way as the measure, therefore they compete and then they can change the location of the saddle point. And the statement of universality is that correlation functions of light operators only know about some coarse-grained features of the heavy operator. For instance, in GR, this is just an analogy, but in GR we have like the mass, the spin, and the charge of the black hole that determines everything. So what we're after is there such a phenomenon in matrix sequence? Okay. Now let me talk about heavy operators. So I'm going to talk about a few classes. The first one is characters of a single matrix. So these I denote by chi r of x, where R is a Young tableau and x is the matrix. So these operators are they're convenient basis and they're orthogonal in some measure. So this R is a Young tableau as x. For instance, I'm not writing down the exact formula, but with some simple determinant formula. But for instance, if the Young tableau was a rectangle, then you get a stack of determinants where the rectangle was n by k, then you get k determinants. Similarly, if you have a trapezium Young tableau, it's something simple again, which is this stack of determinants times van der Waals-like factor, but with a plus instead of minus. Okay, so these are just two examples of heavy operators that you could consider. Note that they're manifestly n order n squared and k scales with n. Okay. Another class you could consider are what are called coherent states. So these are unitary integrals parameterized by these matrices Ji, and they are invariants because you're integrating over the unitary. Right, so and these were introduced in this paper by Berenstein and Chan Wang in 2022, and they were studying some VPS operators in impulse 4, but we're going to use them as some heavy operators for our matrix integrals. Okay, so there's one more, let me just skip that. Now, let's consider a simple example, which is a stack of determinants, right? So I have determinant of x to the power alpha n, and this again has alpha n squared number of matrices. So it is heavy. And now when you write down the standard point equations, these two terms are what we had before for the vacuum without the heavy operator. And I have a new term alpha over x which just comes from varying the determinant. Okay. So the equation we want to solve is this at strong coupling lambda. Now note that this extra term, what it does is when x goes to 0, it blows up. So it's like you can think of this as an electrostatic problem, and this alpha over x gives you a force away from the origin. And therefore the density will no longer be at least it won't be a parabola at the origin, it has to be something different. Okay, so let's try to analyze that equation. So firstly, this term is also the same thing as what I had before, which came from the strong coupling of the integral. And on the right hand side, I just put together everything else. And I assume that there is a single cut solution for the at large L. And I assume that the cut is at x0 minus L to x0 plus L. And I need to solve for this x0 and L. So basically, if you expand the right hand side in L, what you see is that at leading order you get x0 minus alpha over x0, and then there is an order L term and then an order L squared. Right, so notice that the left hand side is small because you're in strong coupling, and the right hand side starts at some order long thing. So what we need is this term to vanish, which means x0 by w plus minus square root of alpha. And therefore, so this is gone, and what remains is again something linear in x.
X is like x0 plus L. How is the second term proportional to that one?
Oh, because x is x0 minus L to x0 plus L.
Okay, so x is within L. How do you know that x0 minus alpha over x0 is not the order L? Can you do more than that?
Sorry, say it again. X0 minus?
Minus alpha over x0. Why can't it be of order L?
It could be. So what I'm assuming here is that there is a solution where this is order 1 and this is small, and then we see self-consistently that is true.
Sorry, you're deriving that you have a parabola centered at each of these points, plus or minus root alpha.
That's right, yeah.
But then the plot where this is shown is called two-cut solution, even though you get this.
Yeah, so let me do that. So the point is now what we did is assume that there is a single cut and you get a parabola, and that's this first one. And you can do a similar analysis for two cut, but I did not do that. But when you do that, what you see is that there are two parabolas centered at plus minus square root of alpha. And even that matches with the numerics. Was that your question?
So, yeah, but for one cut you only get plus root alpha?
Yeah, okay, so there are multiple saddles firstly. One is a single cut at plus root alpha, and then you have a different saddle which is one cut at minus square root of alpha, and then there's another cut which is two cuts at plus minus.
I see.
So it's just different saddles. It actually turns out that two cut is dominant, but it doesn't matter. In any case, the main point is that it's still parabolas, even though you put this stack of determinants. And what changed are the parameters of the parabola, the center and the support.
You are expense to first order.
That's right, yes. Yeah.
So it's not kind of obvious that will be a parabola because we're integrating first order that x squared.
Yeah, it's not exactly a parabola. There are corrections, but they're suppressed at strong. Okay, so then let me look at one more example. So here I'm just going to present the results, but the analysis is very similar, which is if you take a trapezium, which is again this bunch of determinants times random one with plus sign, and you repeat the analysis, you find again that it's a parabola, it's centered at some new position with some new support, and you can again check with the numerics and degrees. Right. So this is nice, but you could say maybe it's an accident of having only some simple operators. So we would like to check it for more general cases, but the saddle point equations get more complicated because for a general M tableau you don't have such nice formulae. So instead, let's move to the second class of operators, which were coherence.
I don't want to slow down that. I can say why x0 has to be equal to. I asked you a question and I didn't understand the answer. X0 minus alpha of x0. Why does it have to be 0?
Because
Why does it?
so alpha is order 1. So how could you, this we want to be small.
Yeah, but not 0. How do you put 0?
Because because it's not suppressed by small parameter. If x0 is order 1, then this would be
I
order
just
1.
want x0 to be equal to plus or minus alpha squared alpha plus something proportional to alpha.
Okay, so you,
What does that violate?
right, so the center you could have small fluctuations in the center, but that's a subleading correction to the density. Right, you just move the parabola by a small amount, that's,
It's still going to be a parabola.
yes. Okay. Okay. So now if you look at coherent states, which so here I just take a particular case which is J2 is 0 and J1 equals 8, and I just inserted this heavy operator which was the unitary integral. And if you remember, there was actually a u integral with j, u, x in that, but I just absorbed the u's into x so that you can even think of this j as a classical source now. So you have a fixed external matrix j, and it's and then you have this integral. Now you could now repeat the same analysis earlier, which is diagonalize and integrate out. And when you do that, this is what you get. Now notice that this time you can't get rid of the u integral because the angle between j and x is relevant. So you have to keep that. So now for what you can, this u integral is actually a well-known integral, which is the Harish Murali integral, the NCIZ integral, which is the following. Written out. And in fact, there is an exact formula at finite time for this integral. So it's something nice. It's a determinant of this matrix, the IPJ, e to the IPJ, sorry, over 1 dimensions of n. Okay. Now, so the exact formula is known, but what we want is the large N limit. And if you try to just naively plug this into saddle point equations, it becomes really messy and we don't know how to solve it. But the larger limit of NCIZ integral actually has a nice physics to it, which is that 1 over n squared times log I is given by the action of a one-dimensional fluid flow. So let me explain what this means. So firstly, so you have one space dimension and then you have time, of course. And I define this function f, which is the velocity of the fluid plus density of the fluid times pi. And this function obeys this equation. It's called the Hopf equation. Anyway, so the idea is you have a one-dimensional fluid, and this fluid obeys some boundary conditions, which are that at this end, at t equals 0, the density of the fluid is the same as the density of eigenvalues of A. And at t equals 1, the density of the fluid is the density of eigenvalues of P. So the claim is if you compute the action of this fluid, then it gives you the H6 integral, which is very notable. Now, it's a much simpler formula. Right, so let's see the slide.
Just try to send it to online. Is anybody checking? Can you stop it?
Because people can ask questions by speaking up in this.
I'm sure they can, but is there any way to reduce the size of the slide so that we can see who's on Zoom?
Okay. I think he did something to not have that happen. Figure out what this is. Alright.
You can see participant. Just click on the participant.
There are.
Okay. So Pedro, Pedro, can you hear us? No, I just wanted to make sure everybody was still alive. Okay, fine. Okay.
Alright, so, where was I? Right, so we want to solve, we want to plug in the HCS integral as a fluid, and I'm going to skip all the details because I'm really out of time. But the idea is when you do that, you can use some integrability properties of fluid. So this one-dimensional fluid that I mentioned is actually integrable, and using the conserved charges, actually you can figure out that there exists again a self-consistent solution to Saddle-Point equations, and it's again a parabola when it's one cut, and the center of mass of the parabola, the x naught, is given by the trace of the matrix J, which was the source, and the support of the parabola L is given by this formula. So notice that again it's suppressed by this large lambda to 1/6, and there's also this factor which is 1 minus the variance of J, and so notice that this blows up when the variance of J becomes equal to 1. So there's some critical phenomenon happening here. So as you make J larger, I guess, when you increase the variance of J, after it hits 1, it's the solution of course breaks down, and we call the universal parabola phase before phase transition as the black hole phase. So notice that no matter which J you put, until criticality, you always get this sort of solution. So let's look at a particular example. I take the source J to be uniform distribution from 0 to alpha, so it's a line distribution. And in that case, you get x naught is at alpha over 2, and L is given by this formula. Okay, and we can do again numerics for this case. So what we see first of all is the criticality is at this 3.464, it's around 3.5, and up to the critical point, the numerics again agree with these analytic parabolas, which are the dashed lines. And this deviation here, the criticality is just because the coupling isn't large enough. Okay, and then after the phase transition, we have non-universal stuff here. Okay. So this was for a particular source, but it's a good indication because we tried 3 cases, and for all of them it turns out to be a parabola in the strong continuity. So any questions about this?
So the parabola is some approximation.
It's strong continuity.
Saying that an infinite coupling is an exact parabola independent of L and independent of the other parameter.
L actually scales with the coupling. So when lambda goes to infinity, it's going to be very, very small.
So I'm just trying to understand, does an error bar in the parabola or not?
Oh, what, sorry?
What do you mean by universal? So,
It's universal in the sense that there are only 2 parameters, right? The x naught and L are the 2 parameters that fix. So by the way, so once you know this density, all light operator probes are fixed. So
I'm just trying to understand that relative to the black hole. So lambda plays a role what in the black hole?
lambda, for instance, if this was a holographic theory, then it would tell you what the size of strings are. In n equals 4, the size of the string goes as lambda to minus quarter.
So lambda goes to infinity?
Is going to the classical.
Lambda goes to infinity is classical. I thought it was n equals to infinity.
Okay, well, it's classical gravity without any string corrections. It's just GR.
Oh.
Okay. Yeah, but what I mean is strings become infinitely massive and they decouple and you just have GR. Okay, so let me now talk about, so far we've been talking about densities of X, which was only one of the 2 matrices. We could ask what happens if you put probes that involve both X and Y, if you want to compute expectation values of lat operators of this sort. product of x's and y's in various orderings. So firstly, one question is, do the matrices commute? So when you go to strong coupling, naively it seems probable that the matrices would commute. It actually turns out to be true. So you have the action with the commutator square term multiplying a large number, so that commutator square better be suppressed. In higher dimensions, this turns out to be not true, but I'll get to that hopefully. Right. So firstly, so the idea is we can show that these matrices commute in strong coupling, and therefore the result only depends on the number of x's and the number of y's, because you can just put them together. So okay, now, and you can derive this fact. The main idea is that the propagator for the y integral is simply it's a Lorentzian, and at strong coupling it becomes a delta function. And using this fact, you can actually look at some Feynman graphs and show that this is true, but I'm going to skip the details. But the idea is you can define joint densities, eigenvalue density of x and y, because they commute. There's a notion of joint eigenvalue densities. And that turns out to be of this form. So when x has a parabolic density, y also has a parabolic density with a different support. And Lx is related to Ly minus. Yeah, so here I'm talking about the joint densities, but you can, for instance, integrate out x and you get a parabola for y, integrate out y, and then you get a parabola for x. Okay, and this is ellipsoid for the joint distribution. Okay, so far we've been talking about sources made out of only x matrices. For instance, we looked at determinants of x, the other characters, or even coherent states which had source for x only. Now, what we need to make sure is that when you put y as well, there is still universality. So notice that when you do that, the y integral is no longer Gaussian, so we can't just integrate out that matrix. So many of the analytic results we don't have any longer. So what we did is we used Monte Carlo to study these cases. And this paper by Raghav Jha was very useful for us for the numerics. Right. So I'm not going to describe what HMC is and so on, but the idea, of course, is that you need to sample from the probability distribution over these matrices, and you do that numerically in some way. So in order to make sure that the Monte Carlo is doing the right thing, let's first revisit the example that we just looked at, which is a line source with jy equal to 0 and jx being a uniform line. And I'm doing n equals 100 and lambda equals 300 now. And this is the result. So this is before criticality. Remember that when the line becomes very long, there is some critical point, and this is before criticality. When you do that, here I'm plotting, so in the red dots are eigenvalues of jx, and the blue dots are eigenvalues of the matrix x plus I1. Okay, so this is what it looks like. The support is clearly an ellipse. And if you compute now the densities of x and y, so here I'm plotting essentially a histogram of from the numerics, which is the solid line. And the dashed line is the analytic prediction, and they both agree with, so they both parabolas of the right sizes. Okay, so that's a case that we already saw in a simpler way earlier. So now let's look at, maybe I can see this. You can see again that there are nice plots and things agree. It's another case that works. So now let's look at actually a two-dimensional source. By two-dimensional, I mean that you have heavy operators of both x and y. So I consider jx and jy to be diagonal matrices, and they're distributed inside a square. So these red dots are the eigenvalues of jx plus ijy. And as I increase the size of the source, I am always getting this. It's a disk, so the eigenvalues of z are always in the disk. And you can again compute the histogram of eigenvalues, so the density, and that matches with it's a parabola. So the difference, by the way, from what we saw earlier is that as the square gets bigger, you still have the size of the parabolas don't change in this case. So maybe I should, are there any questions?
What's the x-axis of the parabola graph?
It's just so it's density of x versus x. It's density of hyperbola.
Only x.
Yeah. You could also try to plot joint densities, but that's a bit harder than manually do this. Yeah, we did not. But clearly there's this U1 symmetry, which means it's straightforward to promote this single density into joint densities. It's just rotational density, which is unique. Okay, so this was, and again, even for the square, when you make the square sufficiently large, there's a phase transition and it becomes non-universal after some point. Okay, skip that. Okay, so yeah, this let me talk about. So now so far we've been, so we've computed some moments, trace x squared, trace y squared. We can do that with Monte Carlo again. Now, the point is, earlier we showed that Ly is proportional to 1 over square root of Lx, which gives us some condition on the moments. So, for instance, trace y squared would be 1 over square root of trace x squared. So these formulae we derived by assuming there was a source for x but not for y. So naively you would expect this to break down when you have a source for both x and y. But actually, when you so let me explain this plot. This solid line is the expectation from this curve. It's the analytic prediction, and then I did a bunch of cases here. For instance, I did some sources in a triangular region, in a rectangular region, and all of them lie on the same curve. So clearly, this is the curve along which any black hole should lie for these 2 matrix models. Okay. So basically, to summarize, we find that in this 2 matrix model with commutator squared potential, we find the universal phase. So and in that universal phase, the eigenvalue distribution is an ellipsoid, and it depends on only a few parameters. The first one is the center of the ellipsoid, it's the x0 and y0. And the second one is, you can call it a mass, which is the number of eigenvalues in the ellipsoid over capital N. So note that when there's a single black hole, this would be equal to 1, but you could have multiple black holes. I did not show those examples, but basically if you put a bunch of sources in one place, you get a blob around that, and then you put another. You can have multiple blobs, and separately each of them will have a parallel distribution.
So it's less than 1.
It's equal to 1 when there's a single blob, single black hole. If you have multiple black holes, it's always less than 1. Okay, so also you could have these ellipses oriented in different directions depending on what the source looks like. For instance, if you put a line at some angle, it would give you an ellipse along that axis. And finally, you have a spin, which is basically how elongated the ellipse is. And for the vacuum, for instance, it would be 0. Yeah. So basically, I'm talking about L major axis as some way to parameterize the size of the major axis versus minor axis. Okay, so this kind of looks like GR. Spells like it in the sense that you have the same parameters as the universal classes of black holes. But this is just some cosmetic similarity. Okay, so that was for 2-dimensional matrix models. And now you could ask, what about more matrices, more than 2 matrices? Do they also show universality? So let's consider the following model. You have again commutator squared for each pair of matrices, and then I'll put a kinetic term as well. Okay, so let me ignore that part. If I have time, I'll comment about computing stuff later. But the main point is that in higher dimensions, we cannot integrate out some of the matrices like we were doing for the Y. So we must learn numerics. So this is in 3 dimensions, this plot. So it's 3 matrices with pairwise commutator squared potentials. And we do again a Monte Carlo numerics, and we find this solid blue line as the histogram. And once again, it matches with this dashed red line, which is a parabola. We don't have an understanding of why this is true analytically, but clearly it's fitting almost perfectly. Okay, so this was for the vacuum. Now we could talk about putting sources for these three matrices. For instance, let's do a line again. So J1 I take to be uniformly distributed on a line, and J2 and J3 I take to be 0. And when you do that, these are the plots you get. So alpha is the length of the line. So as you increase the length of the line, it remains a single black hole, still an ellipse, but it gets more and more elongated. And at some point, this spin, which is the amount how eccentric this ellipse is, that becomes so large that, and then it splits into 2 black holes, and then later on it splits into 3. Okay, so that's the numerics. Any questions about this? Okay, it's not. Right. So if you remember in 2D, after the phase transition, we got some extended objects that were no longer like black holes. But here, after the transition, it's still just a collection of these blobs. And this is kind of it's reminiscent of this instabilities that we find when you have highly spinning black holes in high dimensions. But anyway, what I'm plotting here is so this is after transition. I have 2 blobs, and I'm separately plotting the density of the first blob, which is the blue, and the second blob, which is the orange. And they both agree with parabolas by themselves. So basically what we're seeing is you get a bunch of different black holes, and each of them looks like a parabola.
And are they supposed to become equal to each other in some kind?
Yeah, so that's right. So the dominant saddle is going to be that. This is a subdominant saddle. Okay. Now, let's keep this away because I'm basically out of time. So here I'm plotting Monte Carlo results for various cases. So I'm doing 2D, 3D, and 4D, which is 2 matrices, 3 matrices, and 4 matrices. And these are like a bunch of different results. So for instance, I'm doing a vacuum, I'm doing some line distributions, doing a case where I put these red dots on a sphere of some size, and so on. So it's just a collection of results. And they, of course, they don't agree with each other. It's different in different dimensions. But if you subtract their center of mass and you normalize by their standard deviation, they all collapse to the same distribution in all dimensions. So that's, yeah, it's very cute. And so therefore we claim that this is the universal thing that we expect. Okay, so that's the main part of the talk. Are there any questions before I get to conclusions?
Why can't you do it analytically for variables to be I mean, it's basically Gaussian integration.
No, it's not Gaussian integration anymore because right. So the difference is you have quadruples. So let's say diagonalize one matrix X you diagonalize, and then you have Y and Z. The commutator squared for Y and Z is now going to be programmatic, right? It's quadruple. It's no longer Gaussian integration.
Yeah.
So yeah, it's just complicated. Okay. Yeah. So to summarize, we studied heavy operators in bosonic Yang-Mills type integrals, and in 2D we found analytically that it should be a parabolic density for one matrix, and yeah. So we also checked it numerically using Monte Carlo simulations. In higher dimensions, we don't know how to do things analytically, but Monte Carlo is still something we can do, and it clearly indicates that we still have universality. Okay, so let me skip that. So now, yeah, there are many questions, future directions that we can pursue. Well, first obvious one is can we analytically derive these parabolas? And the second one is it's to explore whether in supersymmetric Young's matrix models, do they also have universality? One particularly simple example is d equals 4, where you have n equals 4 supersymmetric models. And the nice thing about d equals 4 and n equals 4 is that the Pfaffian that you get from integrating out the fermions is positive definite. So you can, it's very easy to do, relatively easy to do Monte Carlo numerics for that case because there's no sign problem. Yeah, if you do, for instance, if you go to d equals 10, the Pfaffian would not be sign definite, so it would oscillate between positive and negative, and that would mess up the numerics. Yeah, so in d equals 10, we have, for instance, the ICTP model and some recent thing that people have studied, which is the polarized ICTP model. And the polarized ICTP model, in fact, there's some strong evidence that there is a bulk dual to it. So it's still a matrix model. So can we see some sort of can we see heavy operating universality in those models? And there can we make contact with gravity. Thank you.
So what is the clear holographic dual of
Yeah, so what people found recently, this paper by Shota Komatsu, Joe Peridonis, what they show is that the saddle point equations of the matrix integral, they map onto some, so it's a BPS supersymmetric solution in the bulk, 10D, and the bulk is parameterized by the same set of quantities as the matrix integral saddle point equations.
I asked you this question once, but what's the, just without the deviation, what's the duality before deforming?
Before deforming, people said it's supposed to be flat space, but there are, to my knowledge, no clear checks of unpolarized.
There's not clear evidence for flat space, how can there be clear evidence for deformations of flat space?
No, because once you deform, once you put a mass term, we have extra scales. No, but they do find some holographic matching on both sides.
Yeah, can we interpret your results as casting doubt on these original conjectures of dualities for IKKT and BFSS, which are not established as well as ABS-CFT, of course?
So I don't, you have to introduce your question. What are the original conjectures?
Well, one is type 2A on flat space, the other is type 2B. But since you're seeing these black hole-like features for much simpler time models, could that mean that the original evidence for these dualities could have been a red herring, because we could also see this?
No, but BFSS has much more concrete evidence. It's not just yeah. I mean, there you can check many things.
So I thought BSS is supposed to be 11 dimensions, not 10 dimensions.
No, it's 10D, but you can decompactify. Right? So the matrices are 9 plus 1, and I think you can take limits to go to.
Talking about BSS, the original BSS, it was 11 dimensions, supposed to be matrix theory. I mean, it's supposed to be n theory. That was supposed to be 2A. Something called matrix strings was supposed to be 2A. Is that what you're talking about?
Yeah, well, I don't know much about BFSS. Yeah, maybe it is.
No, I think it's 10D, but you can take some limit which takes you to 11D. That was the.
Okay, go ahead, sorry.
Yeah, but so your question was, are simpler matrix models also gravitation in some sense?
Well, I was saying that since you see black hole-like features, even in much simpler matrix models than BFSS and IKKT, could you use this to reinterpret some of the evidence for these BFSS and IKKT dualities as being something that's guaranteed to occur anyway, so it's not really evidence anymore?
Yeah, I don't know. I mean, if it's guaranteed to occur, it is still evidence, I guess. But and also much of
that.
Right.
I thought the supersymmetry is supposed to be crucial, and you obviously haven't used it at all. So.
Right. No, I mean, I'm not saying that these models by themselves have well-defined gravity, but they have this universality. The question you could ask is, for theories with better motivation for holographic dual, is the mechanism for universality the same thing? Is the commutative squared potential what's causing universality of black holes? Yes. Mm-hmm. Yes. No, I don't think people have studied that. So usually, what people have looked at is they try to match correlation functions of the matrix model with string amplitudes without any heavy sources. So yeah, that's something we could ask. What happens if in those matrices, if for instance there's all this new stuff about complex Liouville string and so on, what happens if you deform them by putting heavy amplitudes, for instance? For them, the main thing is the spectral curve. So once you have the spectral curve, they don't care how we got to the spectral curve. Because again, for planar correlators, the spectral curve is all that matters.
So you do something special about these interactions. I mean, it's not the most generic interaction, but
Yeah, having that term seems important. Yes. If you try to do something simpler with quartic terms for interactions, that doesn't work anymore. We see universality takes on.
universality just means that. So the only thing you've done is you've concentrated on matrices which commute, right? That's what the turning that thing large just essentially says that x and y have to commute, right?
So actually, that's true in 2D, but not in the 3D matrix models. I didn't go over that, but basically. So in these high dimensional matrix models, the matrices actually don't commute in the black hole phase, even because it's subtle, right? It's not just saying that. So for instance, what happens? Let's say we talk about the vacuum. What happens is all elements of all matrix elements scale as lambda to the -1/4, and therefore there's no separation of scales between eigenvalues and off eigenvalues. So the whole matrix is small. It's not just saying commutative is small.
Matrices don't commute, that term goes up.
So not if x is just small. If the whole matrix scales as some small power of lambda, then I mean zero is. I guess what I'm saying is if x's are all small, then this is small, even if the matrices don't commute.
It's true 2 dimensions also. I don't understand why that's special about high.
It's not special about this fact is not special about hierarchy, but in 2D, what we see is that there is dynamically a separation of scales between eigenvalues and octadians, but in higher dimensions, that's not true anymore.
Just tell me why. Why is it not true that if x is, if matrices don't commute, it seems that that is highly suppressed?
Now, if all the matrices scale as lambda to the -1/4,
No, I don't want x to scale like anything. I just want to take a generic matrix and ask if it commutes with a generic matrix. And if it doesn't, then that term goes up. Why do you want to map x to scale?
no, so when I say x scales as that means when the dominant contribution from the path integral, from this matrix integral, that saddle point has matrices scaling that way, as lambda to the -1/4. If you put generic just order 1 matrices, you would get some big number, and that just does not contribute to the integral.
Do we have any more questions for Harish?
is accurate n is large or when lambda is large? Sorry, I probably asked you this before.
Saddle point you can do at large n, but there's another step which is large lambda, which makes universality happen.
You say it's obvious, so I believe you. You just say the saddle point for large n. It's obvious. The saddle point for large n is obvious if the saddle point is exact. And it goes
Yeah, that's just that should happen. Of course, it's not always clear because when you have a single matrix, that is trivially true because you can reduce to eigenvalues, and then you have n-dimensional integral with order n squared action, which means that's a saddle point integral. But with multi-matrices, it sometimes can be more subtle, but a larger limit exists is what I'm saying.
So even when it's supersymmetric, saddle point is the only thing.
Actually, I wasn't right earlier. So when you have multiple matrices, it's not always true that you can solve things by saddle point because the number of degrees of freedom is n squared.
And is it obvious or is it true?
There are multi-matrix integrals where you can't do saddle point.
The ones you're considering, you can always do it.
The 2D one I considered was the 2D one I could do saddle points for eigenvalues, but for general dimensions for d bigger than 2 I cannot compute using saddle points. I did not use saddle points. I was using Monte Carlo for high dimensions.
You have in Monte Carlo.
Yes, all these plots of them. This is from Monte Carlo.
In Monte Carlo, you say that it's clear that
Okay, so is the question about this commutator squared still or just generally how to solve it?
I don't understand what the claim is. So, the claim is if you include this quartic coupling, then you almost always get this density distribution. That's
the claim, yes.
And it's true in any dimension.
Yes.
And you write your model.
Sorry?
You did these two dimensions.
We did d equals 3, 4, and did d equals 5 vacuum without any heavy operators. All of this
for
were.
n dimensions. Don't know that.
I don't know that. Okay, sure. What I do know is in 3 and 4 it is true, which we have given evidence for.
Then you have some phase transition.
Yes, so yeah.
So it's universal unless it's not.
Yeah, so we need to understand better how to characterize this phase of universality. There is clearly a phase where things are determined by just a few numbers, and then there is a phase outside. But that's also true, for instance, in GR. Right? We have black holes, we have.
I still don't know. I mean, we keep saying GR, but you haven't given me any reason why this should have anything to do with GR.
Sure, but I'm just giving an analogy in the sense that there are sometimes universal phases and non-universal
Why should
phases.
I care what happens in GR? Why is it relevant to GR? That's what I don't understand. Suppose you got a different result. You tell me GR is wrong or something like that.
No, I wouldn't.
So why do you say?
I would just say that this is not a good time, but this is telling me that there are some features like being determined by a few numbers and this fact of when the spin, as I defined it, if the spin increases at some point, it kind of splits into multiple blobs.
I think that's fine. I just don't understand why this is related to logography.
Because in all the microscopic models, well, in many of the microscopic models that we have holographic duals for, this commutator square does show up, and you also have to go to some coupling.
For example, suppose, head dual sounds about some. There are some matrix models which are related to CFTs, right? We know that's all. They're related to something like
The 2D gravity models here.
and you claim that the large lambda limit is somehow related to going to gravity.
So there, the gravitational dual is not really. Yeah, it's more like a Volchy theory. It's not the.
So it's still help you.
Yeah.
Doesn't. I mean, the four-dimensional case for me is just so far away from what you're doing that I don't know how you can get intuition from that. The two-dimensional case, I would think you might be able to understand what this universality behavior is coming from. So maybe it's related to gravity, but I just something not clear to me that's related to black hole not having air.
Yeah, so the careful statement is that it's that we are observing that for many heavy operators, the expectation values of light operators in those backgrounds are determined by a few things.
Okay, that sounds reasonable. So Pedro, you're still there, right? Okay, I mean, this seminar's finished, right?
Yeah.
Can we switch the subject to IKKT? Can somebody tell me why people are taking these models again more seriously?
Yeah, so from what I understand, the flat space, the original IKT model, there's almost no evidence for. People just domesticate use one PFSS one more time. So you have the matrix.
I don't think the BFSS, they start with type 2B, not with type 2A, but go ahead.
Okay. Yeah, but the action you get from reducing PFSS.
It's not, it has different chirality, the spins have a different chirality, but that's okay, but in any case, it's the difference between type 2A and type 2B, it's type 2B.
Okay.
Why, so BFSS, the word, I mean, 2 years of papers where people did find things that seemed to relate it to 11-dimensional supergravity. And the whole problem with BFSS 10 years ago was that they couldn't describe compactification. So they just found that if you describe 11-dimensional supergravity when they tried to compactify, they couldn't get in. That was the main reason why people started working on it. But IKKT, nobody ever worked on it. That's why I'm asking, except for IKKT. That's why I'm asking, why are people interested in that?
I think the exciting feature there is that there is no time. You can have emergent time in the bulb. That's one.
So model, what is it? What physical model is it related to? Why are people interested in this? That time. So did you mind? Can you say what the massive terms they added to the model? No, just I know the IKKT model. I'm asking what terms did they add to the model? What's the massive terms they added, you said?
So they add. So firstly, they break SO10 to SO3 times SO7. So they give different mass to 3 scalars and another mass to the other 7 of them. And Yeah, it's still has the same amount of supersymmetry still.
So it's zero-dimensional supersymmetry, is that why you're doing it?
No, it's 10D supersymmetry.
Then I know that model. What kind of term are you looking at with 10-dimensional supersymmetry that breaks SO10? And then
So I remember they said that it's F4. I don't know what that means, but that's the algebra.
so F4 is a group, is that what F4 is?
Yeah.
There's also a supergroup. And they're different.
So you have, so the supersymmetry algebra you start with is, I assume, SO10 supersymmetry. It's the usual flat space SO10 supersymmetry.
Right.
The terms you add, so you break kappa symmetry, okay, that's okay. And you dimensionally reduce, that's okay. You just everything, nothing depends on,
No, you still keep all the fields. You don't.
no, you don't have, nothing depends on space-time, right?
Yeah.
So you dimensionally reduce, right?
Sure, yeah. But I thought you were starting from ICTP, which is already dimensionally reduced.
Sorry.
So are you talking about how we get this mass deformed ICTP from
Before the
ICTP?
mass, I'm just trying to remember the original model.
Okay.
The original model is you just treat the x's like your gauge fields. So you have 10 x's. I think you get rid of just half of the thetas, you have 16 thetas, is that right?
Right.
So the gauge fix the kappa symmetry, but you still have the usual space-time, 10-dimensional space-time supersymmetry. X goes to constant, theta goes to a constant, and then x goes to theta. So those are the usual things. And now you look to add a term which gives mass what term? What term do you want to add?
So now you add mass 1 times x1 squared plus x2 squared plus x3 squared.
So that breaks the supersymmetry that, for example,
That breaks rotation, SOD rotations.
So the original model is what? It just has, so you see there's no time dependence. So it's just, it just has the 4 commutators, it just has a commutator square and
And then you carve out for
and the U-carve term. That's it.
Yeah, that's the original.
That's translation, right? Under x goes to x plus a constant.
Yes.
Now you add x squared. Isn't that great translation, right?
Yeah, I mean, you.
So that breaks supersymmetry. Supersymmetry.
No, it's a new supersymmetry. It's not the same.
What's the new one?
Yeah, I mean, I don't know the details, but what I remember is they call it this F4 supergroup.
So F4 is a subgroup of the original supersymmetry, or what?
I think it's a different set of supersymmetries in it. It's not like it's not the same.
Yeah, very soft share screen. So maybe you can see that. Yeah, okay. Let's show.
Like, it doesn't seem like there's anything 10D about that.
One is fine, that's the one that I'm used to seeing. Okay, and it says it preserves the 16 supersymmetries, which also get deformed. So what does that mean? It preserves it, which also get deformed. So it doesn't preserve it.
It preserves the number of supersymmetries, but you
So it deforms the 16 supersymmetries. Is that what it's trying to say?
it still has 16 supersymmetries, not the
No,
same
no, look, it
ones.
says it preserves. Can you write, look what 2 is? What's 2? Yeah, one second. So it says, this is what I'm reading what it says. The deformation preserves the 16 supersymmetries in 2. Does it preserve those 16 symmetries or not?
So you need to go for 2. And
No,
then
it doesn't. It deforms it. Is that what you're telling me?
Yes.
Okay. So it's written incorrectly. It deforms the 16 supersymmetries, leading to.
They're still exact symmetries. That's what I'm saying.
Yeah, exactly means it's a symmetry. I don't want to know process. So it shifts psi by an additional term, depends on x, and it also, of course, breaks the translation symmetry, right? So,
let's see, so
terms they add, and do they explain? Do they explain why they write down this terms and not other terms? I mean, is there some explanation, or is it just, oh, let's try this because it's interesting?
Yeah, I mean, I guess I think, yeah, because it still has 16 supersymmetrics, that's probably why.
No, but there probably are hundreds of millions of terms you can add which deform the 16 supersymmetries to something else. The point is that there's no, the supersymmetries are, I guess, zero dimensional, you call them. Because supersymmetries close to themselves, right? They're, so they don't generate translations. The supersymmetries have nothing to do with translations. If I commute two supersymmetries, what do I get? I get delta x. Okay. Okay. Yeah, I think it's matrix in the DMN, I remember. Yeah. I think the BMN was based on the SS, if I remember correctly. So the commutator. So the commutator of two supersymmetries is like a gauge transformation. So it doesn't shift x by constant, but it seems like it shifts x by commutator. It's like taking, right? The commutator of two supersymmetries give you epsilon rho x mu with x rho. So normally delta x mu would just be epsilon mu. But now it says delta x mu equals epsilon rho, commutator of x mu with x rho. That probably. Now there's going to be an additional term. It's going to be omega. Sorry, what's the question?
I don't know, but maybe this was studied by the paper by Olivia. I should look at it. I don't know. The question was, is there a supersymmetric two-dimensional matrix model?
I don't know, this says 10, you want 2 instead of 10? I'm just missing the point.
Yeah, that's the question. It's the 2D version of a supersymmetrized Yang-Mills.
So obviously you can't have the term science if you do that 2 names.
Right.
What is it? Omega has some dimensions and right, omega squared. Oh, I see. Omega has dimension of that. And omega goes to 0, you're telling me a singular, is that what you said?
Yeah, that they compute some moments and then they see that. So you can compute moments with localization before deformation and after deformation, and they don't agree with you to do this.
And this looks like what you were saying, you have to put in the x squared in order to make it make sense of the model, right?
Right. But actually, that's not quite true because even without x squared, it's a finite integral. It's a finite integral. In 2D, what I showed was that it's divergent without the mass term. But here it's finite even without a mass term.
What does it mean it's finite without the mass? What is finite?
The partition function. Yeah, only the first couple of moments. Right.
So then, and you think the supersymmetry is somewhat special, or is what Connor said relevant? Maybe if we just forget about supersymmetry, just look at the x's, and what do I learn by including the sides? How does supersymmetry help you?
Because you can do localization.
At
least for them, right?
Exact. I see. So they use localization to find exact results.
Yes.
I see. Yeah. The deformations they were discussing were the ones which are supersymmetric. I think you told me the supersymmetric, these are supposed to describe supersymmetric deformations, not generic deformations of flat space, right? No, but sorry, I thought you told me that people thought this was dual to some deformed flat space where the deformation preserves some supersymmetry. describe this here? Finding the dual geometry table here?
It's not a just paper. It's
It says finding the dual geometry before. Sorry? What is the dual geometry for? It says finding the intersection. Oh. Yeah. No.
this section 4 is.
No. I'm asking about this. I'm asking about the dual here. I just want to see what it says about this. If you have a solution. You said it's complicated. I just want to see how complicated.
It's in the other paper where I showed.
And these solutions were known before, or were they used?
I think they were solved in some other context and they borrowed some of the results. What are these functions? Let me see if I write it down.